Okay, thank you very much. And thank you everybody to come back after this terrible talk. So I will present joint work with Bao Leung and Stefano Mora. So since it's a 2-hour talk, I could not make it in 3 parts. So it will be a 4-part talk. So I can adapt a little bit. So the first part, I will try to introduce the object and explain the main result. Then I will need to introduce some notation in order to make everything clear, because I will present in a very general way the result, not in precise way, but so I need to present the object more precisely, because it will be something that you know better than me. This Emerson G stack, which play a central role in this talk. So this will be my my first hour talk, I hope so. And then I will give some application of the result and some idea of the flow. I hope so. So let me begin with the first part. So I will be more precise with the results, with this title. It will be a result on local model. And I need some general notation. I had to give this talk for talk on this subject for Rapoport's birthday, and he told me, "You are in Germany, you have to define everything." So I still believe that Heidelberg is in Germany, so I will try to define at least something. Okay. So, the main object in the whole story is this ring. So first, I will define this object and this one, and I will say a few words on this one, and then I will define this one. You see, that's 3 parts. So P will be a prime big enough. So big enough means P with will be bigger than 5, and later P will be bigger than under 5. And so you see that I will make it precise. So right now P is not 2 and 3. It's always better to avoid P equals 2. Then K will be a finite unramified extension of degree small f. OK will be the ring of integers. I will denote K the residue field. Okay, and I have a Frobenius 5 on OK. Okay, it's not that crazy. And I will need also the absolute Galois group of this field. And also the inertia group. K bar is a closure, separable closure of K. I will need an element of K bar, which is P, the F minus 1 root of minus P. And this allows me to define an important character from GK to the invertible element of OK, which is defined to G. I will look at the action of the element of G through this element. Okay. And you can prove that it is independent of the choice of pi. Okay. And it works also if I take for K prime an unramified extension of degree 2. So I will denote F prime, the degree of K prime, or K prime, the ring of integer, P prime, and everything. So you can imagine that you have also this kind of element because this is equal to F. Okay. It does not work. What? Huh? W omega K. It's not good. No. Okay, it's not good. No, but okay. So you have okay, it's completely wrong. Okay, thank you for mentioning it. So you have an action of GK of okay in this way, and so it allows you to define this element. So, I'm so sorry. It said thank you very much. No, it was completely a nonsense. Okay, thank you. So, okay, so this is my my field K, and I need a second field E, which is another finite extension, but I assume that this extension is sufficiently large, but finite. So O will be its ring of integer, and I will denote F this residue field. And so I will fix an embedding of K in E. Since I assume that E is big enough. And I will denote the other unbending, which are given by the composition of this one with probabilities. So, so I have a degree of K such unbending. So I will denote of K in F, which are the same because I assume that E is big enough from K to E, and I can see it like a cyclic group order F. Okay, and I will denote omega F. It's sigma 0 times this one. It's allow you to define this one. Okay, and so this one go from GK to plus. Okay, and in the same similar way, you have this element. Okay, so that's for so to summarize, I have one field K, which is a p-adic field, and I have another field, okay, which is big enough, and I have this element with an important role. So now I am able to define what is this object, the tau. So my tau will be a tame inertial type. So what is first an inertial type? So this is something for K over O, and this is an homomorphism from the inertial group to GL2 of O, such that it has open kernel. And we assume also that it extends to the veil group that I did not define. It's the right group, but okay, I will not define what is the right group, but I will give you some the example which I like the most. So, and in fact, only examples that I will use. So I will need to I don't need to define precisely what is this object. So, for example, so is the power. It's the sum of two power of my character like that. Or two is the sum of two power of this one. And you will say that, okay, this is the same as the previous one. So in order to avoid that this one is the same as the previous one, I will assume that P F plus 1 does not divide H. Okay. So this is the two examples of inertia type I am interested with. But it's too simple. So I will rewrite the same object in a more fancy way. So it's not only because it's fancy, it's because it's more efficient to think that this theory could be generalized. Okay, so I will rewrite these two objects in another way. Okay, so I didn't define what was a inertia type, but you should say that I did not define what was a tame inertia type. So tame means that they factorize through the tame inertia group. Okay. So now the hard part, I have to erase the board. Okay. Okay. Okay, so I will first the first example, rewrite it. So for that, I need to introduce two objects. First, a family of this set. This set is nothing else as a set of permutation for a set of two elements. So this is nothing else as the Veil group of GL2 here. So you can see if you want to go to dimension n, you just have to replace sigma 2 by sigma n. Okay. And mu is also a F set of two integers. Okay, and once again, this is a group of characters of the torus. So you just have to replace by the character of the torus in order to have the single dimension n. So now for this one, so if the product of my element is 1, then I can rewrite this inertia type in the following way. If C of S mu where gamma is given as a sum like that. That's like G mu F minus G. Okay. I'm sorry, not very convenient. So this is a permutation of a set of two elements. Okay, this is a couple of integers. So I have to choose which one I take. There is two coordinates. So I choose the image of one through this permutation. Okay. Okay, that's not very nice, but it's a way it can be generalized. So it has a cost, and the other one is the same. And I take the image of the, so I choose one. So I have mu, which is a couple of integer, and I choose one depending of this element. And this gives you the exponent of each character. And if the product of this element is the permutation of order 2, I have a similar formula for the H here, which is given by a similar sum. So first, I sum the PG for this kind of element plus PF minus 1, PF, sorry, PG. Okay. No? Okay. Okay, no, but it should make sense. But it's the only point is it's not it's to see that this to summarize. So I need an inertial type, which is an homomorphism from the inertia group and GL2 of O, and it's parameterized, in fact, by two elements, this S and this mu. Okay. Okay, and then, in fact, we have a nice way to write everything. So we may, in fact, assume that mu is small, in which sense? Remember that mu is as an element of like that, but in fact, we can assume that this element is a family of. I can assume that this one is 0, and I can assume also that Kg belongs to 0, p plus 1 over 2. So, and also so what I say is that any, this is a French way to rewrite, but it's a big mistake because I have a black. Okay, so you can write your inertia type. You can choose a mu like that, such that your inertia type can be written like that, this times omega f to the power n. Okay. So when tau is of this form with a small family of k, we say that this is called small. But what I say is any inertia type can be written as a product of a small inertia type and some power of omega. So from now on, I will assume that my tau is small. Okay, and I forgot this term, which does not pay me any. Not a central role, in fact. Okay. So from now on, I will assume that my inertia type is small. I will also assume that my type is not scalar. which means that gamma is not the same as gamma prime. Okay, and we'll assume also that it has a niveau, the French name, so level, but it's a niveau, even in English or in German. So it has a niveau F, which means that it has really this form. Okay. That means that this gamma is different from gamma prime modulo PF to the power F minus 1. Okay. So I did part of the job. I define the tau. So let me now introduce the gamma representation. So this is the gamma representation. This is a continuous homomorphism from GK to GL to GK to GL2 of F. This F is a residual field of E. So it means that if I restrict to inertia, I can rewrite rho bar as something like this. If rho bar is irreducible, or something like that. I will keep the gamma for N1, for example. Something like that. If rho bar is reducible. Okay. So that's all for rho bar. And now the deformation ring. So we are interested with the lifting of this rho bar. That means representation such that when you reduce modulo P, you obtain the previous one. This one is irreducible. That's why I added 2F. Yes. Well, I should take another name. But, okay, you can imagine that is gamma prime if you. But yeah, okay. So let's keep it. But the point is when rho bar is reducible, something can appear here. That and here the main point is the star here. But thank you for letting me emphasize. Star is important here, and the star is 0 here. Okay, so this is a lifting of rho bar, but we are interested with geometric lifting. So what means geometric? So in a very precise way, it means potentially Barsotti-Tate with typed tau. But so it's was in my title, but I will not define this notion. It is due to Fontaine. In fact, Barsotti-Tate representation is the same as the crystalline representation with H-Tate weight 0 and 1. And I don't want to go to Fontaine theory, but I will just tell you that it's the same. So we have an equivalence of categories. It's quite a definition if I give you an object, which is the same. So this is the same as a Baroque kissing module of type 2. So I will not define right now what is this object, but I have enough time. I will define it in 20 or 30 minutes. Okay, so just wait a little bit. So the main point here is that kissing introduce so this object, which is a deformation ring for this kind of geometric lifting. So this ring parameterize all the lifting of row bar, which are these nice properties that I didn't define yet. Okay, so we are interested with this kind of lifting of row bar. They are very important because they are related to many conjectures, and they play a central role in the Langlands, the periodic Langlands program. So the main point is that kissing shows that there is one object, one ring, which parameterize all this geometric lifting. Please? Yes, exactly. So this is the row bar, this is the toe, and you may ask, what is this sign? This is a good question. This is eta, and this eta means Barsotti-Tate. Okay, so eta is like BT if you want. That is the usual way to write the weight, in fact, 0 and 1. Okay. And now, what? I would like to say a few words what we know about this ring. I say that this ring is very important. Really, it's related to many conjectures. And so what we know. So, in fact, there is two cases. The first one is when exactly. Yes, but I will make this point precise when I will define the Baroque kissing module of type 2. So right now, I just want to say that my lifting are parameterized by toe and row bar. That's what my point. And then I will explain how I explained how the representation plays a role, but I didn't define show you how toe plays a role. But you have to wait a little bit. But I know that you already do. Let's play this character. I'm a teacher and you are a great student. But I know that you know better than me. So thank you. So when toe is generic. So what means to be generic? So it means that, in fact, you can write the periodic digit of this element. And you assume that the periodic digits are away from 0, 1, p minus 2, and p minus 1. Okay. And so, in fact, the difficulty is really at the board. Generic is at the middle. And why it's so difficult? Because you know that after 0, you have p minus 1. But that's what we like in the periodic theory. So That's why these cases are so difficult. But if you assume that you are away from this case, so you have a very nice result from Emerton, G, and Savit, and by De Long, Levin, and Mora. And from this work, we know that this deformation ring can be 0, or, and we know exactly when it is 0, or it has this form. So a ring, a formal ring with a variable, and also some other variable. This one. Oh oui, this is not the integer. So thank you. Thank you. Yes, thank you very much. And we have this relation. So what I say in the generic case, that the ring is 0, or it has the form, and we know exactly when it is 0, and we know exactly also how many variables we have. Okay, so the situation is nice. But in fact, the non-generic case is not so clear. So it's a number of equation, in fact. So there is some exactly, and all the situation can appear n equals 0 or n equals f if f is odd. So maybe I have to assume that our bar is reducible. Okay. And when tau is non-generic, so only a few. Yes. So I will give you my favorite example. And who is this one? I'm not sure because I put some water. I think that this is this exponent. And so in this case, with Xavier Caruso and David, Agnès David, we prove that the deformation ring was this one. And at this time, we are very happy. Because there is a square here. Sorry, fine. So it means that it is a omega. I will. So this is 2 times 1. Okay, that's 2. This is a 2. F is so it's an extension. So F QP square. F prime. Oh, it's K. Yeah, this. I'm sorry. It's the notation because we use the notation F in this paper. But yeah, we have to adapt. That's the main difficulty. That you have to translate. Yeah, thank you. So, okay, the main point is that we have a square here. Okay, that's so it's very exciting because it means that something happened. Okay, and then we have a series of conjecture. That's again. So the first one is that we conjecture that this ring should be determined by a combinatorial object. So we note subject like that, and we call it the gene. We call it the gene because it tells us how the representation grow up. Okay. It's a natural name. And this gene live in a set of cardinality 4 to the power 2f. So it means that you don't have a lot of deformation rings. So that's part of the conjecture. Only this number of different deformation rings. That's the first conjecture. And the second one was that this ring should be the p-adic completion of a Z algebra that we can explicitly construct from the gene. So what this hypothesis means, this means that in fact, this ring should be independent of P. Okay. That's our conjecture. So you're right. In our conjecture, we assume that rho bar was irreducible. Any in the generic case, this conjecture are true. No, we didn't know. I thought yes, no. For bar generic, we know that we already know that our conjecture is true. Because we have this nice form, and you can see that this P does not play any role. You can change P. No, but you will see. No, but you can consider P as a variable in this formula. You replace the ring O by Z, and so now I would like to present the result. Okay. So for that, I need some more notation. So I will need the Morton G stack. So I will say more about this object later, but let me say that it's a modular stack of the object we are looking for, the Barsotti-Tate representation with same inertial type. And why this object appear in our question? It's because if you take a point on this stack, in fact, you can see this ring as a virtual ring of the stack at Obar. So I will not write this. So that's why this object play an important role. And so we will see a description of this object in terms of subvariety of something. I will denote GRE1. So GRE because it's a Grassmannian and a file Grassmannian. So associate to the group GL2. And so yes. Yeah. Yes. So I take well, I will. Sorry, please.
Yeah, sorry.
Yes, yes, exactly. I look at the Barsotti-Tate point of the Barsotti-Tate part of the stack. Yeah, yes, thank you. I will make it more precise later, but just okay, that you're completely right. Yeah. Yeah. Okay, so I need this Grassmannian. So let me introduce a little bit the notation because it will be useful for later. So if R is a O algebra, I will denote LG of R. So the loop group of this one. So I have to complete for this variable, not V, but I have to take the two of them because I need some more space. And I invert V plus V. And so this is this element, and we take a quotient by this element, but first I need to define this one, and then I will put the one. So this one is the same, the integral part of the previous one. Okay, and you have an evaluation map from L plus G to GL2. You send V to 0, and L1 plus of R is the kernel of this map. Okay. And then you have a stack, which is locally defined like this quotient. Okay. So now I can state our result. Will not have announced my the content of my talk. Because in the show that I can do it. At least I will have states as the main third, so that's it. Maybe I can negotiate a new invitation to Heidelberg. I will be pleased to be invited again. Okay. So our theorem is the following. Okay, so we assume that tau is tame non-scalar, as I told you. We assume that P is sufficiently large. Relatively to F. Then the Mertin-G stack is smooth, locally isomorphic. to an explicit closed irreducible subvariety. I will denote this subvariety like that. Mod is for model, okay, of Goran. Okay. So I will try to explain the statement, then give some application, and then give some idea of the proof. So I will first explain what means smooth locally isomorphic. Then I will say a few words about this explicit part. Then I will say what it means to be sufficiently large. And at last, I will say a few words on the state of art. Okay, so let me begin with the first point. So the H is missing here. So, yeah. It means that, okay. Yes. Okay. Yes, but the point is why you are not very happy is I think it's because in general the notation is X when you in the Emerton-G theory, and the Z is a specific notation for the Barsotti-Tate case. And so all they say it's because the general object in Emerton-G is denoted by X. And in the specific case, Barsotti-Tate is a Z, basically. But you are completely right. I have to assume blah blah blah. But it's already in this notation. So thank you. So what it means, this thing. So in fact, we construct a GL2 of F torsor of this object, and we define also an affine cover of it. I will define later what is how we define this object. But the main point is that we have a local model and we have this object that can be also cut into the same piece, and the two are isomorphic. Okay, so it means that I cut. So first, I take a GL2 F torsor, and I will describe locally this object. That's the content of the first sentence. So now let me discuss what means explicit. So in fact, the local model, this object, is obtained as a P situation of an explicit scheme of a group theoretical theoretic nature. So we will have equation, that means. So that means that explicit means really explicit. So let me say a few remarks. So as you know that Karayiani, Mertenji and Savit have given a bijection between the irreducible component of this object modulo P in terms of non-Steinberg Jordan Holder factor of a representation which is associated to tau. This is a nice version of my small conjecture with Boyle. And in fact, so they give a bijection like this, but it's really explicit. So it means that you could obtain an explicit bijection here. So to each irreducible component, you can say which factor to obtain. So you will say it's not very explicit, but okay. So I will try to convince you that it's really explicit. So it means now, no, it's so it's not. The no, in fact, no, it's I will give you some formula, but okay. But in fact, you know, you have some chart. Okay. Let me. So, so what it means to be explicit? Excuse me. It means that for any error bar, our local model give us the deformation ring for any error bar and any type which are non-scalar. We see a large range of behavior. So, for example, for f equals 3, I will give you some example. What can happen? So it will be something like that. So you can have a 2 like this, but you can also have a 3 like that. So that's fun. you can have something which look a little bit different. So one equation. So it's only to convince you that it's really explicit. Dot x2 y1 plus x 0 plus 1. I'm not sure that I didn't make a mistake, but it had this form, which is not a nice formula. But it could also have this form, which is more fun. I should have a slide for that. And two more I push. Okay. So really, it's completely explicit, and it's very nice because there are a lot of variety of ring, and we can write all the variety, and that there are only a finite number of them. So and so this is what it's for different robar and for it's a different type. Where you see a Z, this is a Z. Yeah, you're right. Okay, this is the parameter of the affine cover. Okay, so so this parameter is linked to these two data, but I will define it later. So the point is you have a way to cut the Mertonji stack in pieces, and the pieces, so to robar and toe, you see one pieces, and then if you have these pieces, you can deduce what is it. But it means that if you give me a robar and a toe, and you give me enough time, I will be able to give you the deformation ring. Okay. And it depends on the F, the time I need. But I think that I am very bad computer. So. Yes, because in fact, for modulo P, yes, so really it's you obtain the description of the stacks. So now and you could be able to translate the irreducible component because everything is explicit. So here, for example, if this formula is correct, I'm not sure it's the paper. You have modulo P, you have 3 different irreducible components, okay, corresponding to each variable, and you can say in terms of the Jordan order of this one, which one corresponds to each variable, in fact. You can make an explicit translation between this term and this one. This is the linear representation associated to two. So there is a way to associate to a type GL2 representation. Okay, so I'm almost done for my first talk. Okay, I have 2 more minutes. So let me say what it means for P to be sufficiently large. It means that P should be bigger than 16 F plus 7. Okay. In fact, we use this hypothesis because we consider an elliptic problem, and we have to kill the obstruction. And to kill the obstruction, we need this hypothesis. We will not say that this is the best number here, but with our technique, we will need such a band because if in fact, if you look at the chart modulo P square or P3, they are isomorphic modulo P square and P3. So you have to go for the power of P big enough in order to see the difference between the two charts. So really, with our method, we will need such a band. Okay, maybe I should stop now.